Today, I've got an interview with Colin Stuart. And Colin is one of the hardest working science journalists that I know. He's been focusing on space and astronomy stories. He's written for everybody, like Sky and Telescope magazine, European Space Agency, New Scientist, many other things. He's written over 20 books. He does astronomy courses. It's kind of amazing. And so with our interview today, it was more of like us catching up, and it was a totally random conversation. But of course, Colin brings a lot of really interesting insights, and the stories that he's been working on are mostly about the sun recently. And so we spent about half this interview talking just about the sun and the latest discoveries made about the sun from Parker Solar Probe, Daniel K. Inouye, Solar Telescope, Solar Orbiter, and so on, and some of the big mysteries that are being pieced together about the sun. But then we also talk about dark matter and exoplanets, and just like a high-level conversation about all of these topics. I think you're going to find it very interesting. All right, here's the interview. Hi, Colin. It's good to see you again.
Thank you for having me back.
So, we've sort of been in very similar circles. You are one of the most productive science writers in this field that I know. Give us an idea of like all the different places that you've published articles, and then we'll talk about your books.
Yeah, so articles-wise, I mean, most of the popular science places you probably would pick up. So New Scientist, for example, Sky and Telescope. I've done things in the past for CNN, and in the UK where I'm based, things like BBC Science Focus magazine and BBC Sky at Night magazine. So pretty much most of the magazines you pick up in a shop.
And some of the recent story topics, like what have you talked about?
So one of the things that I've looked at quite a lot is the sun in various ways, because I've got a bit of a soft spot for the sun. One of my books, and in fact my longest book, was on the sun. And so I've written quite a lot of articles also on the sun, particularly looking at something called the solar abundance problem. So you'd think that because the sun is so close to us compared to all the other stars, that we'd know it pretty well. But actually, it's still a real mystery, and there are some big things we don't know about it. And at the essence of the solar abundance problem is that there are two ways to work out what the sun's made of, particularly how many metals it has. And you may know that to an astronomer, a metal is anything heavier than hydrogen and helium, right? So a chemist is going to disagree with you. But for an astronomer, anything heavier than hydrogen and helium. But there are two ways to work out how many metals the sun has, and they disagree with each other, and they disagree with each other quite strongly. And there's the helioseismologists. They're the ones who use the vibrations inside the sun to work out what the sun's made of. There are the spectroscopists. So they break the sun's light up and spot those telltale absorption lines, those dark bands. But those two methods, they don't agree with each other. And the stakes are really high because we use the sun as a benchmark for all the other stars in the universe.
So if we get the sun wrong, then we might be getting our ideas about all those other stars could be
all
off
the other
as well.
stars, but even things like exoplanets. If we're talking about the habitable zone of exoplanets, well, that's based on the size and the mass and the temperature of the star. And if you're getting that wrong because you've got the sun wrong in the first place, well, then you might be saying, well, I've got a habitable zone planet here, but you haven't, because so everything hinges on it. It's quite a big deal.
Well, I'm interested in talking about these methods. So let's talk about those two methods that astronomers use to try and figure out what the sun is made of. Let's start with the astroseismology. What are they doing?
So in the same way that we use the way that earthquakes move through the earth to work out what's going on inside the earth, we call that seismology. We do the same thing with the sun. There are sound waves inside the sun because things are churning around and moving around. And these sound waves, they're very attuned to temperature. So in the same way that you might if you played a guitar string in a cold room or a hot room, it's going to sound slightly different because the sound waves are traveling through different temperature of air. It's similar for the sun. So if there are more metals, for example, then that also changes the temperature and the way that the sound waves move through the sun. So they're quite a sensitive way of working out metals.
And like with the Earth, geologists can figure out what the different layers are just through the way the seismic waves are moving through the planet. And so are there different densities of elements or different kinds of material in the sun at different depths?
Yeah, it's how we got a pretty good idea of what the structure of the sun is. We think that the core takes up about the inner 20 to 25%. Again, that comes from the helioseismology stuff. Two layers above that, the radiative zone and the convective zone. Again, that comes from the helioseismology. We can even see sunspots on the back of the sun.
I was just going to mention that. Yeah, that this technique is so sensitive that they can see the far side of the sun purely through the seismology, which is
because the way the waves get bounced around. So it's a really, but it's a tiny variation. So the Soho, for example, which was our kind of first dedicated solar observatory back in the 1990s, as the sun throbs in and out, the Fraunhofer lines of the sun, that's those dark absorption lines, they shift, they wobble as the sun is pulsing, but they shift by a quadrillionth of a millimeter. And yet, even in the 1990s, we had, and Soho still works to this day, has the ability to pick up those ridiculously small changes. So the precision required for this kind of stuff is, it's mind-blowing.
And so what does that technique tell us the sun is made of?
So originally, there wasn't this dispute between the two teams. When these measurements were first made, they agreed. The spectroscopists and the helioseismologists said, well, the sun's about 1.8% metal. So 3/4 hydrogen, 1/4 helium.
Right. And then metal could be lithium, oxygen, platinum, you name it. Yeah.
Mostly things like oxygen. But yes, anything heavier than hydrogen and helium. 1.8% metals. The rest largely 3/4 hydrogen, 1/4 helium. But then when the spectroscopists started to make more advanced measurements, and this is kind of based on modeling as well, so they can't just look at the spectral lines and get a straight measurement. They have to model the thermal equilibrium of the sun. When they did that, they suddenly said, okay, we're going to drop down to 1.3% metals.
And sorry, just to give people an explainer on this spectroscopy method, what are they doing there?
So this is breaking up the light from the sun, and you get the classic rainbow that you'd expect, just like a raindrop breaks up sunlight. But the key difference with the sun is you see a series of dark lines within that rainbow spectrum. They're just gaps. They're missing colors. And the reason why those colors are missing, that light is missing because it never left the sun to reach the earth. Those different elements within the sun swallowed that particular color of light. So
that's why they call them absorption lines.
Exactly. And we see a gap or a space where that light should have been, but it is missing. And if you look at one of these, look at these spectra with the black lines, they look quite a lot like a barcode.
Yeah.
And that is basically what they are. Scanning these spectra, they tell us what the sun is made of. And so when they did that more accurately, suddenly they were saying, well, now, hang on a minute, not 1.8% metals, 1.3% metals.
Right.
Well, hang on a minute, it's 0.5%, right? We can forgive 0.5%, but
right. That's
this
a
is
rounding
0.5%
error. No problem.
of the sun. So it's the equivalent to 1,500 Earths worth of mass.
Right. Like that 0.5% is almost equivalent to the mass of the rest of the solar system combined. So there's a lot of mass there.
Yeah,
right.
1,500 Earths. And it means that the metals play a kind of oversized role in the sun. So fewer metals would mean that we would decrease the mass and the radius of stars by about 10% and the age of the sun by about 20%.
Now, the people that are doing the spectroscopy, they're imaging the surface of the sun, as you said, taking its chemical fingerprint. But the assumption is you're only seeing the surface of the sun. It would be like measuring the consistency of an orange by measuring the color of the skin. It doesn't really tell you what's going on inside just the stuff that's on the surface. While the astroseismologists feel pretty confident that they're seeing what's inside the sun and using that to extrapolate. This definitely sounds like the grounds for a vigorous debate.
Yeah, so I wrote an article about this for Sky and Telescope magazine, and I was lucky enough that it won the American Astronomical Society Solar Physics Media Award, because as a writer, it's just a joy to be able to tell. You get disagreement in science all the time, but it's rare to come across something where the two teams are very politely, but at the same time very forcibly saying you're wrong.
Yeah, no, relentlessly we can't disagreeing.
And yeah, it was beautiful to have these quotes of people saying, "No, this is a spectroscopist's dispute. We got it right," and but then the others go, "Well, no, hang on a minute."
So what are the implications then, right? Like if the seismologists are right versus the spectroscopists are right, what are the implications for the universe, our understanding of other stars?
So as I said, about a 10% decrease in mass and radius of stars and a 20% decrease in age or lifetime. So the sun, for example, would die much quicker if the spectroscopists are right. And so we wouldn't have as long to live in the solar system. So stars would live shorter lives than we've been reckoning on. And so as I mentioned earlier, it would then, sorry.
So like when we look out into the universe and we see all stars and we say, oh, this star is 3 billion years old and that star is 5 billion years old and it has 2 billion years left to live. All of those numbers would have to be modified
by up to 20%. And
by up to 20%, yeah.
And the inventory of a star is actually one of the ways we age it. You know, people might say, well, hang on a minute, how do we know how old a star is? It's the contents. Because when the universe began, the Big Bang created hydrogen and helium. That's why the universe is largely 3/4 hydrogen and 1/4 helium. That's what was set in between 3 and 20 minutes after the Big Bang. The only thing that could change the dial on that afterwards were stars. When the first stars came along, they started churning that hydrogen and helium into things like carbon and nitrogen and oxygen and some of the heavier metals. So the very earliest stars had very few metals. But as the universe aged, stars began to go through their life cycles, explode, spread their contents into the universe. Iron, for example, something produced at the very last minute of a very massive star, it goes supernova and it blasts that iron into the universe to be incorporated into new stars. So the younger a star is, the more metals it has, because it's been around long. The universe had been around longer before it formed. So the earliest stars very pristine, very low metallicity. The youngest stars are much higher metallicity. So these metals, even if we're talking about 0.5%, it has a big impact on some of these things like the ages of stars.
And it's weird. I mean, not weird, but I mean, we're at this point now where the math says that those giant first stars had to have been there because we can see the after effects. We can see the heavier elements that are in the stars. We're sitting on a planet using technology that was formed in the furnaces of stars, and in some of it was those first stars, and yet we see no direct evidence of them so far. So all we have are mathematical models and giant supercomputers that are grinding through to try and figure out what these things are. But we're right. We do finally have a tool that kind of brings them just within our grasp, and that's Webb. Through gravitational lensing, we may actually be able to get those first signatures. And I think I've even heard some papers, people starting to say, like, maybe we've seen some signatures of some of the supernova fingerprints of those first stars. Do you think we'll get a chance to find out more about them soon?
I really hope so, and I do think so. So that was there's been a kind of fundamental limit in the past of seeing those first stars, because the Hubble Space Telescope was great. It allowed us to peer back a long way into the universe's past. But you could build Hubble as big as you like, and it still wouldn't have been able to see those very first stars, because the universe is expanding, has been expanding since the Big Bang, and stretching the light from those first stars as it travels towards the Earth. And it stretched so much from the earliest stars that it's now beyond the visible part of the spectrum, past the red end of the spectrum into the infrared, which is where Webb comes in as an infrared telescope. So for the first time, we should hopefully be able to see these first stars. There have been some clues before Webb. There was this amazing, it's quite controversial, so it's by no means a done deal, but there was this amazing low-tech tabletop experiment called EDGES. I wrote a feature for New Scientist about it several years ago. It was in Australia, and it was looking for when the first stars lit up, their intense ultraviolet light would have ionized the surrounding hydrogen gas. So just to make sure I'm not using any jargon, right? The ionization is when we got our classic atom with the nucleus and the electrons. Ionization is ripping those electrons away. And so ionizing the hydrogen in the early universe. There was a signal that said, we found that signal of ionization. And it was earlier than people had thought at the time. And so that seems to be the growing trend, both from the first stuff from Webb, although it's very tentative so far, and even from EDGES, seems to be saying that stars formed a lot earlier, or at least at the very beginning of the range that we originally thought, maybe something like 100 to 150 million years after the Big Bang. Whereas before we were talking at something maybe like 300 million years was the estimate. So these tentative observations are saying, well, hang on, the first stars seem to have formed fast.
Well, and that matches the observations from Webb showing galaxies that seem to be in the few hundreds, 250, 350 million years after the Big Bang. They've got stars in them, so it's definitely seems feasible that there could be stars forming in those. Now, there's some amazing new solar telescopes that are out there. You've got the Daniel K. Inouye Solar Telescope here on Earth. You've got Parker Solar Probe. You've got Solar Orbiter. How is our understanding of the sun going to change, do you think, in the next few years?
Well, all those things you just mentioned, they work in tandem with each other. So sometimes people think about Solar Orbiter is a European Space Agency mission. Parker is a NASA mission. You might be thinking these things are competing with each other, but it's really more about collaboration because they're doing different things, but it means we have a very joined up approach now. So I guess just to recap, Parker, its approach is to go really close to the sun. In fact, it's already gone and touched the sun, touched the corona, the outer atmosphere of the sun. But because it's going so close and the temperatures it has to withstand are ridiculously high, it can't have a camera. It can't have a visible light camera. It can't take photographs. It can sense things, but if it looked at the sun, it would just blind itself. So Solar Orbiter, though, is further back. And at that distance, it can have a camera. And so if we're looking at things launching off the sun, for example, say either a coronal mass ejection, a CME, big mountain-sized wad of solar material spat into space, a parcel of solar wind blown off the sun, we've got the whole package now. We can sense it as it comes past Parker, see it from the solar surface outwards from Solar Orbiter, and then even DKIST, which is a 4-meter mirrored solar observatory. Yeah. Before that, we had a 1-meter mirror.
Yeah, it's a ludicrous piece of technology. Yeah,
is a huge, because it's the square, right, of the gathering power. So it's a huge jump up. And some of the images from DKIST of the solar surface kind of bubbling up. So we have a really joined up system now. And I guess some of the mysteries that we'd like to solve, I guess 2 avenues. One, there's the practical dangers of the sun, and then there's the mysteries that we'd like to know as astronomers.
Well, let's talk about that practical. I mean, because the sun is responsible for keeping Earth habitable on the surface. And so if we didn't have the sun, then we wouldn't have life on the surface of the Earth. And yet the sun is this giant thermonuclear reaction that's going right over there. And it's kind of terrifying to think about it.
Yeah, and I guess we grow up and we learn at school that the sun is a good thing, as you say. Like it's a benevolent friend that gives us the heat and the light that we need. But it's 150 million kilometers away, and it can burn your skin. So that's telling you that it's quite an intense object. And it can also be very dangerous. So
I always like this idea, that if you had air in between us and the sun, it would just be this constant screeching noise that deafened everything you could hear, because the sound waves coming from the sun would be so loud. And thankfully there's vacuum in between us and the sun. Otherwise all we would hear is just the sun yelling at us all day long.
Yes, but thankfully space is quiet. I guess one of the stories of the sun and the sun's power and how much of a foe it can be. When I was researching my Rebel Star book, which is the book about the sun, there was this wonderful story about the Vietnam War and Richard Nixon. So Vietnam, obviously a very famously attritional war, a very difficult war to win. He was looking for something to give him an edge. So with his generals, he hatched a plan to drop sea mines into the waters in the Gulf of Tonkin off the coast of Vietnam. The idea being that when the supply ships were coming in to deliver food and supplies to the Vietnamese, that they would trigger the mines and it would sink the ships, and maybe he could starve the Vietnamese out. That was certainly the plan. Except he gets a phone call in August 1972 to tell him that the mines have exploded and there were no ships anywhere nearby and no ships sunk whatsoever. It was the sun. The sun exploded the mines. That month, there was an enormous coronal mass ejection from the sun that arrived on the Earth. And there was so much electricity coursing through the Earth's atmosphere that it tricked the mines. It triggered the mines and they exploded. So the sun can even get involved in our geopolitics. That's how much of a foe it is.
But I mean, we've talked about in the past on this channel about the Carrington event back in the 1800s where telegraph towers were set on fire. And that was a time when the Earth wasn't interconnected and dependent on all of this electricity and connections. Now we have fleets of satellites orbiting us. Every house is connected to another house across vast grids. What would be the impact of a really powerful solar flare to the planet?
If we got something of the level of the Carrington event, it would be one of the most noteworthy things, I think, to happen on the Earth for a very long time. Weirdly, it would kind of be there are these two things called corona, right? And so I was talking about coronal mass ejections long before COVID. And then along comes another corona-based thing, which, by the way, is to do with the word for crown, the shape of the sun's atmosphere and the shape of the virus. But the coronal mass ejection is kind of its impact on our daily lives is the kind of reverse of COVID. So in COVID, we weren't allowed to go anywhere. We were stuck inside, but at least we had electricity, and at least it didn't happen 20 years ago. At least it happened now when we had Netflix and Zoom and all the things we've relied on for. Whereas a coronal ejection would be the exact opposite. You would, in theory, be able to go wherever you like, although what transport you use might be interesting. You could walk anywhere you wanted, and hug anyone you wanted. But we're talking about months, power off for months. So I, again, wrote an article about this once, and I spoke to the person at the National Grid, which is here in the UK. That's the body that sorts out in charge of keeping the lights on. And yeah, it would take minimum of 3 months to get the lights back on, because the main issue is transformers. Transformers are the things that ferry our electricity around, move it around cities and across between cities. If you've ever seen one, they're massive. They're as big as a house. And what would happen is that the extra electricity would cause them to melt, the oil in them to catch fire. They'd stop working. We don't have a lot of these things hanging around because they're so massive. So we'd have to somehow rebuild all of these transformers, and that's a kind of minimum 3.
And the factory for building the transformers wouldn't have any power.
Exactly. So you've got an extra problem. So you'd have to go on backup generator power, or even just things like you just start digging into the practicalities of it, just sort of kind of logicking it out. Hospitals. Mm-hmm. Hospitals are going to have backup generators, but they can't get through the same workload that they get through now. So, go into schools and give talks, and one of them is about our how space affects our daily lives, even if we're children. And I talk about, well, if you break your leg or you burn yourself or cut yourself and you're not, it hurts, but you're not in danger, your life isn't threatened, you're not getting seen. That's just, you're not on the list.
Right.
If you have a heart attack or you're in a kind of car accident and it's life or death, generator power will be used for you. But for the other stuff,
broke your leg, walk it off.
Wait.
Yeah.
Splint it
Now,
and wait.
Now you mentioned, that studying the sun like this, obviously there are these practical purposes, but then there are sort of the more just basic research understanding of the universe. So let's talk about that.
Well, I guess the biggest mystery of the sun is also the corona, actually, that outer layer of the atmosphere we've been talking about, because there is something called the coronal heating problem, and the essence of it is the corona is way too hot. So temperature-wise, in the core of the sun, we're talking about 15.7 million degrees. By the time, we know that, by the way, because of neutrinos. The neutrinos produced in the center of the sun are an amazing thermometer, because if you change the temperature even slightly, the number of neutrinos changes dramatically. So,
it's interesting.
That's that. Because I get asked that all the time. I thought I mentioned it.
How do we know? I actually didn't know that. That's awesome.
I can't remember the exact number, but if you, it's a lot. Even changing the temperature by a few percent, the neutrinos changes dramatically. It's really sensitive to temperature. Mm-hmm. So 15.7 million degrees in the core of the sun. By the time you get to the surface, what we call the photosphere, that's where the sunspots are, and that's the bit we see in the sky. We're talking more like, say, 5,000, 5,500 degrees. But then you keep going further from the sun out into the corona, which is where Parker is kind of touching. And it extends to about 6 or 7 million kilometers from the sun, from the surface. The temperature there can get up to 3 million degrees again. Mm-hmm. Now, you don't need to have a physics degree to know that's not how heat works, right? The source of the sun's heat is in the middle. So let's imagine that we put a campfire in there instead. Right? The sun's not on fire, but let's imagine that the source is a fire. You walk away from the campfire and you cool down, but then you keep walking further from the campfire and then you heat up. We know intuitively that's not how heat works.
Yeah.
So there must be something else going on. We're pretty confident the measurements are right, that it really is 2 or 3 million degrees. So what Parker and Solar Orbiter are going to help us work out is we have basically 2 ideas for what's going on, and it might help us work out which one of those is right, whether neither of them are right.
Well, what are the 2 ideas?
So one is called nanoflares. So maybe you're familiar with solar flares, these big, not to be confused with the prominences, right? The prominences are the kind of flame-like things that lick off the sun. A flare is a very rapid, intense and localized brightening of the sun. It's magnetic energy being released. Nanoflares are the same thing, exactly the same mechanism, but 1 billion times less energetic, hence the nano. So each tiny nanoflare isn't going to inject much energy into the corona at all. But if there are enough of them going off in concert around the sun, then together they might be heating up the corona. And we've had a bit of a tease from Solar Orbiter, because it has seen microflares on the sun. So still not small enough to be the nanoflares, but certainly heading in the right direction. And so they call them campfires in a way, tiny little campfires going off, injecting heat. That's one idea. The other idea is something called Alvan waves. And an Alvan wave is a wave along a line of magnetic field. So the sun's very magnetic. Some of its field lines are open. That means they don't loop back into the sun. They go straight out into space. And just as you can think of them as like waves on an ocean. If you're at the beach, a wave can carry, say, a surfer and dump them on the sand. Or equally, an Alvan wave, which is a wave along one of these lines, can carry energy out and dump it on the beach of the corona. Again, we've seen some Alvin waves and things like Parker has seen these things called switchbacks, where the direction of the magnetic field sort of switches back one way than the other, kind of S shape. So there are hints that both of these things are going on, but it's still, we have still not conclusively said, you know, which is the dominant one. So I think from people I've spoken to, the solar physicists that I've spoken to, I think most people think that both of these things are happening. The question really is, which one is the dominant one?
The answer is yes. I talk to people even about dark matter, and you know, the question is always what is it? And I think the consensus is that it's probably a whole bunch of things all together, that it's a little bit of this and a little bit of that, and maybe a few primordial black holes and a little bit of axions. And when you add it all together, you end up with the combined effect of dark matter. And same thing with the solar heating problem of the sun. It would make the most sense if it is some of one and some of the other, which makes it really difficult to just identify which of the ones is the primary factor.
Yeah, and I think it's unlikely to be 50-50. I think there's going to be something that's very dominant. So with the dark matter stuff, if we want to go off on that tangent, then we're at a little bit of a crisis point, I think, with that stuff, because the main thing that we thought dark matter was for the last 20 or 30 years, we really should have found it by now if it was that. But the lengths that we've gone to try and find these particles, we've dug through the ice in Antarctica to put detectors down there. We've built things in abandoned gold mines. We have strapped something to the International Space Station to peer at the center of the galaxy. And
accelerated particles in the Large Hadron Collider.
All of this stuff, and we've still not found one of these WIMPs, which is to this point has been the kind of leading candidate for dark matter. So we were talking before about this kind of science denialism, or there's a lot of pushback when something like this happens, and people kind of celebrate it and they go, "See, you didn't know what you were talking about the whole time." But that's a kind of, scientists know that. Like, they're not claiming otherwise. It's how else do you proceed? Like, you make a guess. You make an informed guess, you do an experiment to see if you're right. And if you're wrong, you go, okay, well, I'll try something else. Like, it's not, it happened with Webb too. We talked about Webb earlier, this whole kind of thing that came out about how Webb disproved the Big Bang. And no, we're quite happy with the Big Bang. It's just things happened a little earlier than we thought. It's a window dressing, right? So there's been it's always been there. I'm noticing a lot more of this kind of, I don't know whether I'm just getting more of it sent my way or not, but it's growing, I think, this kind of...
I can describe it exactly for you because I see it as well. The gist is, you do a story about dark matter and you get a comment on your thing about you scientists, and it's in a very kind of condescending tone, don't understand, haven't thought through, you have some kind of almost religious position about your thinking, you're not open-minded, and the idea of dark matter is just dumb. That is like if I sort of add all the themes together. And I think we live in this time when many things that were unsolved, things that were mysteries to people 50, 100 years ago, we now understand. Electricity, relativity, how the sun works mostly. And yet, of course, there will always be stuff that is at the cutting edge of science, right? As soon as you answer questions, you now have new questions, and now you go and try to answer those. And you're going to live in this uncertain world as you make progress. And the low-hanging fruit has been picked, and now you have the high-hanging fruit that's left to try and figure out.
Although I guess in some ways it's very... I can kind of see why, if you look at it objectively, quite often when we have a big mystery in astrophysics or cosmology, we kind of we go, okay, well, we can make it all work if we invent something invisible.
Yes, right. And I think from people's perspective, they're like, people say, well, couldn't it just be UFOs is causing this thing that we see? And the answer is yes, it can always be aliens, because aliens can do whatever you need them to do. Whatever you want aliens to do, they could do it. And therefore, it is not an answer because it's everything. It's magic. And
I thought I'd heard pretty much every wacky UFO thing going, but I've never heard UFOs as an explanation for dark matter before.
Well, not even just dark matter. Like could UFOs be an explanation for Boyagan Star? Could UFOs be an explanation for Oumuamua, right? And the answer is sure. Yeah, totally. Absolutely, right? But because if the aliens have an undefined and unlimited capability to do anything in the universe, break the laws of physics as we understand them to their whim, then you could literally explain everything. Just whatever you want, you can explain with UFOs. Why did we not get any rain today? UFOs. Why did Google cancel Stadia? UFOs.
I guess the response I always have is I wish the universe were that interesting. Because whenever we do solve these things, the answer is always the most boring answer, which is fine. But chances are it's not the sexy, interesting thing. Chances are it's the really dull, mundane thing. But,
Paul Sutter has a great thing he says. He says, if it's interesting, it's probably wrong, which I love. And so with dark matter, right, you've got this thing that has a name that's a terrible name because it's assuming that it's dark and it's assuming that it's matter. But it could very well be neither of those things. It's like black holes,
right? I guess
right?
It's nearly 100 years old, isn't it? That was 1930. So at the time, I can't imagine that Fritz Zwicky, when he came up with that name in another language also, was kind of setting himself up for the next 100 years of... But no, I agree. Yeah. I mean, then if dark energy is bad, if dark matter is bad, dark energy is worse, right?
Yeah, and like black holes, right? They're neither black nor holes. And yet the name is there. I mean, with the Big Bang, at least you've got half of it, right? It's definitely big, but it's not a bang. So I think when people see dark matter, just when they hear this idea, this concept, they leap to the conclusion that astronomers have figured it out and are in denial about something. But I think they overestimate how far along this journey scientists are. They're in there's absolutely something going on here phase, because they've got an enormous amount of evidence that things aren't working according to their theories. And they're totally open to the idea that their theories are wrong, but the evidence is overwhelming that there's something out there. And
we've got probably I can think of easily 3. There are more.
Together we could probably come up with 10. Yeah, lines of evidence.
Independent things as to why this. In fact, I can think of So there's lots of independent things that point towards it, but it is slightly embarrassing that if you put together the dark matter and the dark energy, that's 95% of the mass energy of the universe. If you're an astronomer or an astrophysicist and you're, I suppose, professing to at least in part understand the universe, if you're only able to accurately say what 5% of it is, it's a little bit of a strange situation.
Yeah. And I think people, it makes them, I don't know, mad, dismissive, suspicious, skeptical, which is fine. So new,
isn't it? I mean, the dark matter stuff really, although it was 1930s originally, was only around about 1980 and into the 80s that it became a seriously considered thing. And then the dark energy stuff was 1998. I mean, give people a break. They've only had a couple of decades to figure out what it's basically.
Yeah. I mean, and I think part of it is just because it plays, as you say, it's 95% of the universe based on the current observations that are made, is that we understand 5%. We don't understand 95%. Astronomers wish they could, but they don't. And they are at least willing and humble enough to say, we don't know what this is. And I think that is to be respected. That is to be applauded, to say, that you're willing and just humble to admit that you have no idea what something is. You know that it's there, but you don't know what it is. It would be like going to a mechanic. And I always use this analogy, right? Because you go to a mechanic and you're just like, my car makes this sound and I don't know what it is. And the mechanic says, I don't know either. Let's figure it out. And you know there's something wrong because the car doesn't work properly, but you don't know what it is. And that's the place. And you have to be in that place to make scientific discovery.
That's the fun part. And I was saying to you before, I think before we started, that what I love so much and what is always, what made me want to do this for a living and moved from the child who was, obsessed with space to someone who does this for a job now, was just the ingenuity and the detective work required for astronomers and astrophysicists, because all scientists are, detectives, but you have to be extra clever, I think, with space, because you don't have, okay, we sent probes to the planets, but we can't send probes to other solar systems yet or other stars. The only thing we have to go on, when we were talking about the sun, for example, we can't, even Parker can't go inside the sun. So we have to tease out these things from helioseismology or spectroscopy. We have to piece together the scant clues we're given by the universe. So I think rather than kind of attacking them for not knowing, I'm not a research astronomer, right? I'm a astronomy writer, so I'm not sort of standing up for them for my own, if you like. I write about their work, but that ability just to, like you say, be open to new ideas and just go where the evidence is kind of taking you, I think is to be applauded, not to be
yeah, because it's like anybody who tells you that they have the answer is probably wrong, almost certainly wrong. It's only when you can accept the fact that we don't have the answer that you can move forward together, listening to what nature tells you one step at a time. And I think that there are a lot of these concepts. And I think the one about the helioseismologists versus the spectroscopists, spectroscopers, anyway, is a great example of a serious disagreement in science, where both teams are scrutinizing the work from the other team, looking for any crack that they can find, and also mustering as much evidence that they can to the table. The understood goal by both teams is we want to get to a better understanding of the nature of reality. And each team would gladly accept defeat if that meant that they knew that how the universe worked better.
Yeah,
that's
right.
Science at its best.
Exactly. I think the trouble is we get taught at school that science is just a collection of facts. That's the way it's certainly was kind of presented to me when I was at school. And we need to get across this idea that actually, no, it's like you say, it's a journey. It's a quest to understand and uncover these mysteries. And we're not going to get it right all the time, because who gets it right all the time? We get there eventually, but it takes. We kind of lost the one thing I always think about is the people who built cathedrals. And if you start, or even the big things like the pyramids, those things took longer than a human lifetime to make. So when you started building a cathedral, you probably weren't going to see it finished, but you were part of this team that was building this thing that was going to stand for centuries. I think these days we're very short term in our thinking, and what astronomy really helps with, certainly for me, I'm often talking about hundreds of millions of years or billions of years in the past. It gives you a much wider perspective than the kind of short 80, 90 years we probably get in our lifetime. So yeah, we're not always going to get answers straight away. We should be thinking like building science like a cathedral for generations to come.
And I think just respecting the process and appreciating the process, and as you say, the journey. So what else is sort of attracting your attention right now in astronomy?
There's two things. One is the mean, it's a naturally quite a sexy thing is exoplanet stuff. Again, that theme of detective work, I just love some of the methods that we use to find these alien planets. And we can't see the planet, but we can work out, because of all this logic and detective work, its size and its temperature, and even now with Webb coming up, even more so than before, contents of atmospheres and that sort of stuff. But what's been really intriguing is to watch again, slightly from the outside, being not a researcher, but someone who writes about this stuff, is the kind of reaction and surprise of what we've been finding. Because I think when we first set out looking for these alien planets, we expected to find something familiar. We expected to find us, basically, copies of our solar system. And in fact, most of our cosmology is built on the premise of the Copernican principle that we're not special and that we're just rank ordinary. But at least of the ones we've been finding so far, and it could be a selection bias, there's all sorts of explanations for it, but we have some incredibly weird and wonderful systems that look nothing like ours, but even not just the configuration of the planets, but entire types of planets that just don't exist here. So it seems to us that the most common planets are in between the rocky planets and the gas planets, right? So we have the 4 rocky planets and the 4 giant planets. But the most common planets seem to be mini Neptunes, which are kind of Earth-sized or slightly bigger than Earth-sized gas planets, or super Earths. These are planets with about twice as wide as the Earth, somewhere around there. And we don't have that intermediate planet in the solar system. Why don't we? Does that have an effect on the habitability of a system, for example? So it's been a real surprise, I think, to marvel at how unnormal our solar system seems.
Yeah, we are weirdly unique. I mean, we're only still at the beginning. We've merely found a little over 5,000 confirmed exoplanets, and most of those are the extreme cases. The things that are casting off the biggest signal are going to get detected first. We haven't filled in all of the little pieces around, all the little planets that could be orbiting closer to the star than the hot Jupiter, or farther than the star than the hot Jupiter, the ones that may take a year to go around the star. That's actually a really hard planet to confirm. But
you got to wait a long time. If you're doing it by the transit method of the planet dropping in the star dropping in brightness when the planet gets in the way, you're only going to get a transit once a year. So you've got to be patient. I mean, that's why Kepler, when it was launched, originally had a 3-year minimum window, because that was long enough to see 3 transits of an Earth-like, or at least not an Earth-like planet, but a planet on an Earth-like orbit.
That really is the tragedy of Kepler. It could have been the observatory to help us find that other Earth, to detect that dip of an Earth-sized world orbiting around a sun-like star, but Kepler, its reaction wheels failed too early, and so they had to shift so that it was finding planets around red dwarf stars, which are
even that was
fascinating.
That's just ingenious. I mean, the way that they did that to say, rather than saying, "Oh, okay, we lost it, it's gone," just the kind of ingenuity to use the sun as a reaction wheel. It was just. I've never ceased to be amazed at it's just the weird. Humans are very weird creatures, right? Some of the stuff we're doing around the world right now, not great. but then there's the other side. There's this other side, and that's why I like kind of writing about this stuff, because it's telling the story of, I think, the kind of better side to us. So the exoplanet stuff, and then I really like the gravitational wave stuff too, because that's completely revolutionary. That is an entirely new way to see things in the universe. There are, we've relied for the last 400 years, since the invention of the telescope, pretty much on the electromagnetic spectrum. So that's light all the way from gamma rays to radio waves. And we've done pretty well in that 400 years of using those things to understand the universe. But there are some things in the universe that don't kick out anything in the electromagnetic spectrum. They only kick out these gravitational waves. And so the analogy would be that imagine if you'd lived your entire life in a dark room and you tried to work out what was in the room by feeling around, and you might have an idea of some of the objects in the room and their distribution and what they might be made of from the way you touch them. But then decades later, you've been living in this room for a long time, decades and decades, and someone brings a torch in and hands you this torch, and you start casting it around the room, and you're like, oh, that's what that looks like, or that's how that works, or and that is what gravitational waves are like. It is like giving us a torch to shine on things that we simply haven't been able to see before. And it's so new. I mean, we're talking, it was 2015, the very first one. So we're only 7 years into this. And so when we look forward to the decades to come, things like LISA, the laser-based, so a gravitational wave detector is called interferometer. And so the I in LISA is interferometer, but it's a space-based gravitational wave detector. 3 spacecraft flying in formation, if memory serves, 2.5 million kilometers apart from each other. And that will really shift the frequency of the waves we can detect. Right now, we can only, it's very crude, we're detecting huge waves that come from like crazy cataclysmic events like black holes colliding. But if we want to get the much smaller waves, we're going to need something like LISA. And that opens the door to things like primordial gravitational waves. Because there's a big problem with the Big Bang. I'm not saying for 1 minute that it's the wrong idea, but it's an imperfect theory. It has gaping holes in it. And we have this fix that we've been knocking around for 30, 40 years called inflation. But the problem has always been, well, how do you prove that this thing called inflation happened? It's quite a hard thing to prove, but these primordial gravitational waves might be one way. So I think that we've only scratched the surface with this new way of seeing things.
Yeah, this idea of multi-messenger astronomy is quite exciting. And you mentioned radiation, the one that we've used for all of astronomy, and then more recently gravitational waves. And then you also have neutrinos as this other third way to observe the universe. And same thing, there could be this cosmic neutrino background radiation. There could be neutrinos released shortly after the Big Bang that allow you to probe and detect if inflation was happening. It's really exciting. So again, it's like, back to your analogy, you suddenly have a flashlight and you're looking around the room, and then someone sort of gives you a chance to hear. So you can hear echoes coming from inside the room to figure out where things are as well. So you've got many ways to sort this out. And it's those ways to confirm that with independent lines of evidence that gives you the most progress in science. It's when you have those independent lines of evidence, finally you can make real strides. And it's tricky until you have that. And so it's an exciting time. I mean, I always say we're in the golden age of astronomy, but I think I've been saying it for 20 years now. So
I think maybe every age is the golden age of astronomy to the people in it, because it's always better than it's been before, because we're always going bigger, better. I mean, even if we started doing things like putting radio telescopes on the moon, for example, just that ability to have that quiet will be a huge.
Now you have an amazing breadth of knowledge, and it's funny. Like you kind of feel like a kindred soul to me, because I dabble. I report and write and interview people about the things that I'm curious about and interested in, and I suspect we could have conversations about almost any topic in space and astronomy. And you're running a course so people can kind of follow in on this journey. Can you talk about that?
Yeah. So it's a course I used to teach in person. So I know the kind of pain points people have with coming to this kind of a topic. So people are interested in the kind of things we've been talking about, but so often it's very technical or it's very math heavy. And that puts people off because they get it's kind of the classic brief history of time, Stephen Hawking, right? It's the book everyone has.
Yeah, that everyone gave up. Yes.
Yeah, because you get to a point and then you go, ugh, okay, I'm lost.
Yeah.
And so the premise of the course is that we don't do that. We do all the good stuff. So I go through a lot of the things we've been talking about in the course today. So we start with the sun, and then you fly out to the very edge of the observable universe. So through the solar system, out into the Milky Way, we talk about dark matter, black holes, supernova explosions, other galaxies, the Big Bang, even the possibility of other universes. But again, all without that, basically on the level that we've been talking about it today. It's that the explanations that I've given today are very similar to the explanations that in the course. So it's an 8-hour course. It's standalone, so you can do it in your own time. It's broken down into bite-sized modules. So each one's under 10 minutes long. So you can dip in and you can dip out and do slot a few modules into your commute or your, whatever. So yeah, it's all the cutting edge stuff, but without any of the jargon or the math.
And so where do people find this?
So if you go to my website, which is colinstuart.net, you'll find I've got astrophysics for beginners. And then I've got other courses up my sleeve too. So I'm busy putting together an astronomy for beginners course, which is more kind of practical in terms of.
Yeah, I mean, I like the idea. I mean, there's so many resources out there available on the internet today that you can dip in and kind of wallow in the science discoveries, but it's really hard to kind of place them within a larger framework. You're learning bits and pieces about coronal heating and bits and pieces about exoplanets and biosignatures and SETI and gravitational waves and so on, but it's really tough to see how they all mesh together. And I don't do it for people.
I think this is why but
I think it's important.
Itinerary of the course is set up the way that it is to take you from where you kind of know in the solar system, and it does build on topics. So, for example, it's very much designed to. The reason why I start in the solar system is because I introduce concepts that you're going to need later, but introducing it in a more familiar environment. So a classic example would be the beginning of the course is about the solar system, but other than the sun, that's not strictly speaking astrophysics. But the reason it's there is to kind of build up on these ideas. So looking at the rings of Saturn, for example, why are they there? Well, we think it's because a moon got torn apart. And the rings of Saturn are within Saturn's what we call Roche limit, which is the distance at which, if you go inside it, the difference in forces across an object is so great that it gets torn apart. But using that idea of the Roche limit, we need it when I talk to you about the supermassive black hole in the center of our Milky Way, because it's one of the ways we work out how big that black hole is. Because there are stars going around it that clearly haven't passed inside the Roche limit, otherwise they would get torn apart. So it is, and this comes from both experience of teaching the course in person, seeing faces of where people are struggling, and so it's a bit built on that, but also built on the writing as well. So, more than 10 years of explaining these things in.
Yeah, and so people should just go to your website and put a link in the show notes. But once again, if people want to sort of track what you're working on, see what other educational information you have available, what's the best way to do that?
So two options. You go to my website, which is, as I said, colinstuart.net. That's Stuart. I'd also have a weekly newsletter that I send out on a Monday. So mostly it's space news. It's my favorite space news of the week. It's really random and quite odd facts that I find if I'm researching books and articles and things. And occasionally there is stuff in there about new things I've got going on, courses and so on. But it's certainly not heavy on that stuff. It's more on the news. And then I think Twitter, I'm probably most active on Twitter as a social media outlet. So I'm Sky Ponderer on there.
Perfect. Well, Colin, it's been a pleasure to catch up with you and hear what you're up to. And again, we could have picked anything, I think. We could have picked 1,000 different topics. So these ones are sort of the Venn diagram of the topics that we're kind of most fascinated by today. But talk to us again in a couple of years, and we could be obsessing about completely different topics. But it's been a pleasure to talk to you again. Good luck with your course. Good luck with your journalism, your research, all of the work, and the more books. They're coming out all the time.
Yeah, 20. Yeah. I'm on 20 now. But,
20 books. That's mad.
21 is about to begin next week.
So. Yeah, you're beyond an enthusiast. You clearly are like willing to suffer over and over again to write these books. I mad props to you, man.
Great. Well, thank you for having me back. It's been a lot of fun.
All right, take care.
Cheers. Thank you.